Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, where this is my continuing feature on the Math Lovers book, and I'm up to section 3.3 of volume 1, which is on continued fractions, and this is my fourth lesson on continued fractions. I already talked about, continued fractions of rational numbers, which always terminate, as well as continued fractions of quadratic irrational numbers, which repeat. And today I'm going to talk about some other pretty interesting continued fractions. These are continued fractions of some other irrational numbers. Not quadratic irrationals, and they don't repeat, but they don't terminate because the quadratic irrationals of quadratic continued fractions of non-quadratic of any irrational number don't repeat. So anyway, let's just begin. Like I said, a lot of numbers have really interesting continued fractions. I think a prime example is the number e. And I talked about e a few times earlier. This is something I don't really go into in detail until volume 2. I think it's chapter 11, where I start talking about exponential numbers and logarithms. And e used to be called the base of natural logarithms. It's about 2.71828. It's an irrational number, but it's also a transcendental number. And I'm not going to say any more about it than that. It's a very useful number, though. Just take my word for it. It's considered probably the second most important irrational number after pi. So that should give you an idea how useful it is. It's just that you don't usually use it until you start using calculus. But anyway, you see that the continued fraction of e has a very special form to it. I mean, it starts out 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, and so on. That pattern keeps going forever. It doesn't repeat, obviously, because you have these even numbers that keep growing every third term. You can write it kind of symbolically, though. This is the way that people usually write the continued fraction e. They write 2 semicolon, then they write 1 2n 1 with a bar above it, meaning that n increases by 1 each time. So it starts out 1 2 1 1 4 1 1 6 1. I think you get the idea. And I think it's pretty remarkable that the continued fraction of e has this special form, because most irrational numbers don't have any special form to their continued fraction. The ones that do are pretty rare. But it turns out that there's a lot of other expressions involving e that have special forms to their continued fractions as well. As a matter of fact, if you look at the square root of e, this one has another pattern to it. It starts out 1, 1, 1, 1, 1, 5, 1, 1, 9, 1, 1, 13, 1, so on. You can write this using this other notation as 1 semicolon and then 1 4n minus 3 1 with the the last three coefficients with a line above them. Meaning again, we start with n equals 1 and we keep increasing n each time by 1. And similarly, cube root of 3 has a form that kind of has a similar pattern. It starts out 1 semicolon 1 2 1 1 8 1 1 14 1 1 21, which we can write as 1 semicolon 1 comma 6n minus 4 comma 1. And the fourth root of e has the form 1 semicolon 1 8n minus 5 comma 1. This pattern continues for any kth root of e, by the way. They all have a special form like this. I'm not sure why. But anyway, they do. And there's some other interesting irrational numbers that have interesting patterns to them. For instance, e minus 1 over e plus 1. This one I think even has a simpler form. Starts out 0 because this number is less than 1. It's between 0 and 1. So the floor of e minus 1 over e plus 1 is 0. But then look what happens to the continued fraction coefficients after that. 2, 6, 10, 14, and so on. They keep increasing by 4, starting with 2. So we can symbolize that as 0 semicolon 4n minus 2 with a line above it. So this is a pattern with a repetition of ones of length 1, but it's not a repetition. The pattern has length 1. And e minus 1 over 2 looks almost just like this. This one is 0 semicolon 1 comma 16 comma 6 comma 10 comma 14 so on. Look, notice that every coefficient is the same as for e minus 1 over e plus 1 except for the second one. A sub 1 if you like, it's equal to 1 instead of 2. So you can write this symbolically as 0 semicolon 1 comma 4n plus 2 with a line above it. And I've seen some other pretty exotic irrational numbers that have similar kinds of patterns. As a matter of fact, I think you can derive formulas for things like the continued fraction that starts out as 1 semicolon 2, 3, 4, 5, 6, 7, 8, where each one increases by 1. This one you can actually calculate in terms of modified Bessel functions. I'm not going to even try to explain what those are. But you can calculate the numbers like these exactly using special functions. I just thought I'd mention that. But what about pi? I mean, you might think if E has, in E, all these powers, all these numbers involving E have this kind of simple form to their continued fraction. What about pi? You'd think pi would as well. I mean, but as far as anybody knows, it doesn't. I mean, look at the continued fraction of pi. This is, I think, the first 30 or so coefficients. They don't seem to have any pattern to them, really. And I think millions, probably even billions of continued fraction coefficients of pi have been calculated, but nobody's been able to find any pattern to them. As a matter of fact, I think they passed every test of a random irrational number. If you just picked a random irrational number, computed its continued fraction, you'd see a similar distribution in the continued fraction coefficients. So nothing unusual about them. I mean, I guess it's a little bit unusual. You get this big coefficient 292 for the fifth one. I mean, that's pretty rare that you get coefficients that big, but not impossible. I guess it's just kind of a coincidence that you happen to get such a big one early on. But there's another pretty big one later, 84. Eventually you go high, long enough, you'll find as big coefficients as you want. So nothing special about the continued fraction of pi, as far as anybody can tell. Anyway, that completes my video on other continued fractions. Thank you for watching. Long live math, and I'll see you guys next time. Bye.